Welcome guys. So in this video, we're gonna do the 1.5 linear models, the first day of it. And so we're gonna talk about how do you get how do you identify that a relationship is strong or weak? It's positive and negative. And we're gonna use infinite differences to match different functions to the data charts. So if we look at the first scatter plot here, we see that it is going in a positive direction because as x is increasing, our y is also increasing. It's in a positive direction here. And they're closely knit together. So that's a strong relationship. Over here, they're scattered, so you really don't see a positive or negative correlation here. So this is something that you would call has a no correlation. All right, so if we take a moment to identify each of these graphs, this is positive. It's increasing in the y direction as it is increasing in the x direction. This is also positive. This is also positive. Here it's negative. It's moving down, right? These are moving up, up, up. This is moving down, down, down. So these are all negative. What makes the difference between these three is the strength of the relationship. So if we were to put a straight line through these points, if that straight line hits most of the points, or the points are really, really close to that straight line, then we call this a strong relationship. If we put a straight line through these set of points, we see that the points are a little spread out around the line. So this is a weak relationship. And so is this one. Here we have a negative strong relationship. Same concept applies here, is that if you put a straight line through these set of points, if it's hitting most of the points or the points are really, really close to that line, then it's strong. Here we start to get weaker and weaker again. So that just shows you the visual. And the middle ones are moderate because they're not really strong, but they're not super weak. Okay, so here's a definition here. And that is the correlation coefficient, and it's usually denoted by the letter R. So we usually say R is our correlation coefficient, and what the correlation coefficient tells you, it really talks about how strong or how weak your relationship is in terms of the dots on the scatter plot and your line that goes through them. So a positive correlation coefficient is obviously going to be a positive R. These are positive R's, right? And obviously, I'm going to use another color here. If we have a negative correlation coefficient, your R is going to be negative, right? Now, the main difference here is that if the relationship is strong, your correlation coefficient is going to be close to 1 or -1. So if it's positive strong, it's going to be a positive 1. If it's negative strong, it's going to be -1. Same applies for the weak. Your R is going to be close to 0.5. Again, it's going to be close to positive 0.5 if it is a positive weak correlation, and it's going to be close to -0.5 if it's a negative weak correlation. If we have no correlation, then our correlation coefficient is 0 because it does not exist. And that's something we're going to see later on when we use the graphing calculators to create functions for scattered points. So if we look at these examples here, and we ask the question, would a line be a good fit for this data? So a linear line, right? Would it be a good fit for this data right here? And if we draw a line through it, we see that indeed, yeah, it is a good fit for that data right there, right? If we draw a line through here, we see that it is not a good fit because this set of data points actually curves up as we're increasing in the x values. So because it's curving up, this does not look like a linear function. This looks like something else, right? We'll talk about that later. Here, if you put a line again through this, it is not hitting those points, right? So this is not a linear function, does not represent this data set well. If we put a line through here, the line does fit this data set well. So the first one and the last one, a line is a good representation for those data points. All right. So let's talk about different general forms of equations for a second. So a linear equation is written in the form of y is equal to ax plus b. You guys know this as y is equal to mx plus b. It's the same thing. It's just sometimes they change the m with another variable a, right? It's the same exact thing, right? And quadratic is denoted, and you know it's a quadratic function when you have a squared inside the equation. And so the general form is y is equal to ax squared plus bx plus c, where c is your constant here in the quadratic formula, and your constant here is b. And in a cubic function, you have the same kind of setup, except for cubic means that you have x to the third power, and then you go to the second power and then the first power. Okay, this is really important to know because when we start to have data sets and then we're asked to find what the equation looks like, you're going to need to know what the general form looks like in order to create the equation. Okay, so here's our first example. They gave us a data set and they're asking what function would best fit this data and write the equation of the function. So in order to answer the first part, which is find out what function would best fit this data, we just talked about three functions in the last slide, right? We talked about the linear function, we talked about a quadratic function, and we talked about a cubic function. So how do we know this data set by just looking at the data points? How do we know which function it correlates with? If we were to graph this as a scatter plot, then we can visually see that, right? Just like we did in the first few slides, we visually saw them by looking at the scatter plots. But what if you don't have it set up in a scatter plot, right? What if you just have the data points? So what you're going to do is you're going to do something called the differences, the finite differences, okay? We're doing finite differences. And what that is that you're going to create another column right next to your y values, and you're going to subtract each y value from the previous one. So we're going to do 13 minus 10, and we get 3. 16 minus 13, we get 3. 19 minus 16, we get 3. 22 minus 19, we get 3. 25 minus 22, we get 3 again. After doing your finite differences, if you get the same first difference, then it's a linear function. If we get the same second difference, it's a quadratic function. And similarly, if we get the same third difference, it's a cubic function. All right, and we're going to go over that in the next example. But we see here that our first difference, D1, was all the same. It was all 3. Therefore, this example and this data set is a linear function. And now the general form of a linear function is y is equal to ax plus b. So now how do we write that equation? So we create another table. Let me just change my color. I lost my little yellow. Okay. So I'm going to create another table. X, y, and then the first difference. And I'm going to fill in the same x values that they gave me in this table. And I'm going to put it in here. So that's 2, 3, 4, 5. I think 4 points is going to be enough. And then what you're going to do is you're going to take this function right here and you're going to plug in each value for x in there to get your new y to place that inside your table. So we're going to put 2 inside here. So we get 2a plus b. So you're substituting your values for x inside the function, the general form. So we put x inside, we put 3 inside here for x, so we have 3a plus b. We put the 4 in place for x, we have 4a plus b. We substitute the 5 in, we get 5a plus b. And now we could do the same thing that we did on this table with numbers, but here we're going to do it with the functions, which we're going to do the first difference. So we're going to do 3a plus b minus 2a plus b, right? So 3a plus b minus 2a plus b. So that's 3a minus 2a, which leaves you with 1a. b minus b cancels out, goes to 0. Same thing here. You're going to do 4a minus 3a, leaves you with a. b minus b, 0. 5a minus 4a, a, b minus b goes to 0. So now we could start matching up numbers that are in the same position on this table with the phrases, the mathematical phrases on this table, and solve for the different variables. So matching up the first column, under the D1 column, the first value there, A, with the first value in the D1 column here, 3, that tells me that A is equal to 3. So I can put that inside my equation. And I could take any one of these and match them up with any one of these as long as I am choosing the right position on each chart, right? So let's say I'm going to take the first box under the Y on this one, so I have to take the first box under the Y on that chart, and it has to be the same, right? So now I could set them equal to each other. So I have 2a plus b is equal to 10. I do know that a is 3, so I could substitute that in. So now I have 6 plus b is equal to 10, so I know b is equal to 4. And now I finally have all the information I need to write the equation for this table set. And the equation that gave me these x and y values is y is equal to, instead of a, I'm putting 3, x plus, instead of b, I'm putting 4. And that's my equation for this data set. I would also double check my work by plugging this into my graphing calculator and making sure that these points in the original problem align with the equation that I just made. So the second example is just the same. but this time it's not going to be a linear because I wanted to show you what a quadratic or a cubic equation looks like. So I'm just going to set it up, and then I want you to work on your own to find the equation for this one. So if I do the first difference, 13 minus 4, I get 9. 34 minus 13, that gives me 21. 73 minus 34 gives me 39. 136 minus 73 gives me 63. And I see that the first differences are not all the same number. So therefore, I'm going to rule out that this could be a linear function. So let me do the second difference. All right, so now I'm going to do, let me choose a different color. 21 minus 9, I get 12. 39 minus 18, 39 minus 21, you get 18. 63 minus 39, you get 24. Again, our second difference is not the same, so this is not a quadratic function. So I have to do the third difference. And this is how you set it up. You always go one row down. When you're setting up the differences, you're going one row down, okay? So now we're doing 18 minus 12, we get 6. 24 minus 18, we get 6. So our third difference, we finally have the same difference. And if we have the same difference, then we know that because it's the third difference, this is going to be a cubic function. So it's going to be in the form of ax to the third plus bx squared plus cx plus d. And we need to find the variables a, b, c, and d of this function. I'll start with setting up the table and what it should look like, and then I want you to do the rest on your own. So I'm just going to erase this so I have some room. And you would set up the other table by doing your same values for x, which were 1, 2, 3, 4, 5. Okay, you need to keep your general form in mind, which was ax to the third plus bx squared plus cx plus d. You're going to substitute each one of these values inside this equation. So when I plug in 1 for x, I get 1 to the third times a, which just gives me a, plus 1 squared times b gives me b, plus 1 times c gives me c, plus d. Okay, difference 1, difference 2, difference 3. That's how you set up the chart. You're going to do the same thing for 2. When I plug in 2 inside there, I get 8a plus 4b plus 2c plus d. When I plug in 3 inside this equation for my x value, I get 27a plus 9b plus 3c plus d. When I plug in 4 inside this equation, I get 64a plus 16b plus 4c plus d. When I plug in 5 in for x inside the same equation, I get 125a plus 25b plus 5c plus d. So finally, you're going to do the same thing like we did in the last example, where you're going to find your differences here. So you're going to do 8a minus a gives you 7a, 4b minus b gives you 3b, 2c minus c gives you 1c, and d minus d, it goes away. And then you're going to start to match up. So I kind of don't have room here, and I wanted to have you guys practice this on your own. So go ahead and practice this on your own. But make sure that you create a chart that has enough space, just so you could be able to do all the calculations there, okay? And then you finally get, after you do this, you get that your A is going to be equal to 1, your B is equal to 0, your C is equal to 2, your D is equal to 1, and your answer should be, instead of A, we're plugging in 1, so it's x to the third. Instead of B, we're plugging in 0, so this term goes away. Instead of C, we're plugging in 2, so it becomes 2x, and instead of D, we're plugging in 1, so it becomes plus 1, and that is the equation that matches with this table set. All right, if you guys have any questions, just let me know. I'll see you guys later. Thank you.